In this video, I want to look at higher order partial derivatives. We'll talk about second order partial derivatives first. There is no reason that I can't take a partial derivative of something I've already taken a partial derivative of. For example, I can take the partial derivative with respect to x of the partial derivative of f with respect to x, which is equal to the d squared f over dx squared in partial derivative form. This notation can be expressed as fxx, or it can be pronounced as d squared f dx squared, or fxx. I can also take the partial derivative with respect to y of the partial derivative of f with respect to y, and I get d squared f dy squared. Again, my notation could be written as fyy, and I can say d squared f dy squared, or fyy. We can also take a partial derivative with respect to x of a partial derivative of f with respect to y and get d squared f dx dy. This can be written as fyx, and I will typically pronounce that just as fyx, but we could say d squared f dx dy if we so chose. I could also take the partial with respect to y of the partial of f with respect to x, which is d squared f dy dx. I can write it as fxy, and I can say it typically as fxy. These last two are examples of what we call mixed partial derivatives. I'm taking a derivative with respect to both of my variables in different orders. And order does matter. In a mixed partial derivative, the order in which the derivative is taken can be very important. In most cases, it may not make any difference at all, but in others, it definitely will. So you want to make sure and keep track of the notation and the order that your derivatives are being taken in. For example, in the notation where I have fy in parentheses followed by x, I first take the partial derivative with respect to y, and then I take the partial derivative of that result with respect to x. If I have fx in parentheses followed by y, that's my fxy. This means I'm taking the partial derivative with respect to x first, and then taking the partial derivative with respect to y. It is important to pay attention to the notation, both in terms of reading the problems and in showing your work and entering your results. There is a theory of the equality of mixed partial derivatives. It's also known as Clairaut's theorem. We assume that f is defined on an open set D of R2, and that fxy and fyx are continuous throughout the region D. Then fxy will equal fyx at all points of D, so that you can see by Clairaut's theorem, if either of my mixed partial derivatives fails to be continuous on the region of interest, it's very likely that I won't have an equality of the mixed partial derivatives. Let's work an example. I want to find the 4 second partial derivatives of f of xy, which is equal to the quantity x plus 3y squared. I'm going to take the partial derivative with respect to x of the partial derivative with respect to x of f, which will give me d squared f dx squared. fxx in this case becomes the partial with respect to x of 2 times x plus 3y, which is equal to 2. If I take the second partial derivative with respect to y, I get d squared f dy squared. fyy becomes the partial with respect to y of 6 times x plus 3y, which is equal to 18. For the mixed partial derivative fyx, I take the partial derivative with respect to x of the partial derivative of f with respect to y, which gives me d squared f dx dy, and fyx becomes the partial derivative with respect to x of 6 times x plus 3y, which is equal to 6. And finally, the mixed partial derivative, where I take the partial derivative of f with respect to x first, and then take the partial derivative with respect to y, or d squared f dy dx, gives me fxy is equal to the partial derivative with respect to y of 2 times x plus 3y, or 6. Keep in mind, each time I take this partial derivative, the variable that I am not taking the derivative with respect to acts just like a constant. Here's another example. If I'm given the function f of xy is equal to 3x squared y to the negative 1 minus 2x to the negative 1 y squared, I want to show that fxy is equal to fyx. fxy is the partial derivative with respect to y of the partial derivative with respect to x of the quantity 3x squared y to the negative 1 minus 2x to the negative 1 y squared. I take the partial derivative with respect to x first, and I'm left with the partial derivative with respect to y of the quantity 6x y to the negative 1 plus 2x to the negative 2 y squared. I take the partial derivative now with respect to y, and I get negative 6x y to the negative 2 plus 4x to the negative 2 y. fyx is the partial derivative with respect to x of the partial derivative with respect to y of 3x squared y to the negative 1 minus 2x to the negative 1 y squared. This time I take the derivative with respect to y first, and I'm left with the partial derivative with respect to x of negative 3x squared y to the negative 2 minus 4x to the negative 1 y. I take that partial derivative with respect to x, and I get negative 6x y to the negative 2 plus 4x to the negative 2 y. Both of these are exactly the same. This tells me that my two mixed partial derivatives are continuous on the domain for my function. Now you get to try it. Pause the video and find the 4-second partial derivatives of the function f of xy is equal to the cosine of xy. When you're ready, restart the video to check your understanding. So for my solution, I need to start by first taking the partial derivative with respect to x and the partial derivative with respect to y, and then move forward from there. So I want to find the partial derivative with respect to x of the partial derivative with respect to x of the cosine of xy. This is equal to negative the partial derivative with respect to x of y times sine of xy, which becomes negative y squared times the cosine of xy. The partial derivative with respect to y of the partial derivative with respect to y of the cosine of xy gives me the negative partial derivative with respect to y of x times sine of xy. When I finish out this partial derivative, I get negative x squared cosine xy. The partial derivative with respect to x of the partial derivative with respect to y of cosine xy gives me negative the partial derivative with respect to x of x sine of xy, which gives me negative xy cosine xy minus sine of xy. And the partial derivative with respect to y of the partial derivative with respect to x of the cosine of xy gives me negative the partial derivative with respect to y of y sine of xy, and this gives me negative xy cosine xy minus sine of xy, which is exactly the same for my two mixed partial derivatives. This is how I can find higher order partial derivatives for functions that depend on two independent variables. Be sure and let me know if you have any questions.